Hello everyone, in this video we will continue talking about Newton-Raphson method. We will focus on the halting condition of the Newton-Raphson method. There are three different conditions which may cause the iteration process to halt. The first condition is that we halt if both of the following conditions are met. So there are condition A and condition B. Both of them should be satisfied for us to halt. Condition A is that the step between successive iterates is sufficiently small. Remember that we always start from the initial guess x0, and then based on x0 we find the next approximation x1, and then based on x1 we find the next approximation x2, right? At some point, if we base on xn, we find xn plus 1, and the absolute value of xn plus 1 minus xn is less than a certain constant. This constant, we call it epsilon step. If that happens, we can see that the distance between the two approximations is sufficiently small, which means we moved from x1 to from x0 to x1, and then moved from x1 to x2. And when we move from xn to xn plus 1, because the distance between the 2 points are so small that we barely moved, so then there is no point to do the iteration again. Condition B is that the function evaluated at the point xn plus 1 is sufficiently small. It's the absolute value of xn plus 1 less than a certain constant, and this constant is called epsilon abs. This is similar to the condition B in the bisection method or the false position method, because for some function it increases so fast when we are a little bit away from the actual root. The function value at this point becomes very large, so it's not safe to say that this point is a reasonable approximation for the root. So we need to check in the y direction to see if the value of the function at this point is sufficiently small. Okay, so the second halting condition is that if the derivative f xn prime is equal to 0, then the iteration process fails because we have this division by 0 problem, and then we need to halt. So remember that the formula for the Newton-Raphson method, if you write down the formula, xn plus 1 equal to xn minus fxn over fxn prime, right? So if this fxn prime is 0, then we have this division by 0 problem. We cannot continue this process. The last halting condition is that if we have iterated some maximum number of times, say n, and haven't met condition 1, which means the iteration process does not converge, then we halt and indicate that a solution was not found. An important difference between Newton-Raphson method and the bracketing method, and the bracketing method includes both the bisection method and the false position method. So important difference between the Newton-Raphson and the previous two methods is that Newton-Raphson method may not converge. So by using this method, it's possible that you find the root, but it's also possible that you couldn't find the root. So the process may not converge. In contrast, if you use the bracketing method, the bisection or the false position, there is a guarantee that you can find the root as long as you satisfy the initial requirements. Okay, so because this method, this Newton-Raphson method, sometimes does not converge, so we cannot do this forever, right? So we need to set a maximum number of times for the iteration, say n. For example, n is equal to 100. So we want to do 100 iterations to see if this converges. If it doesn't, then we assume that because 100 is large enough, then we assume that this method will not converge. So we will stop the iteration. If we halt due to condition 1, we state that xn plus 1 is our approximation to the root. So basically, by using this method, we found that this method converges, and we find the root as xn plus 1. If we halt due to condition 2 or condition 3, we may either choose a different initial approximation x0 or state that this method does not converge. Sometimes, if condition 2 or condition 3 happens, we can change to a different initial guess, then run this code again, then it will converge, right? So you can switch to another initial guess, or you can simply say that this method does not converge. Okay, so here is something you should know. There is no general convergence criteria for Newton-Raphson method. Its convergence depends on the nature of the function and on the accuracy of the initial guess. The only remedy is to have an initial guess that is sufficiently close to the root. Okay, so there is no guarantee that Newton-Raphson method with this particular initial guess will give you a good approximation of the root. And if it doesn't converge, you can change to another initial guess. So the only remedy is to have a initial guess that is close enough to the root. Let me show you some examples that which show that the Newton-Raphson method doesn't converge. So for example, we have this function x, y, and assume that it looks like this. And we start from the initial guess x1. No, let me do this. So let's assume that we have a initial guess here, x0, right? Then we draw a tangent line to the function. Right? So this will be x1, right? Then based on x1, we draw a vertical line, and then at this intersection point, we draw a tangent line to the function. So this will be x2, right? And at x2, we draw a vertical line, and this intersection point. At this intersection point, we draw a tangent line. So this will be x3, and then draw the vertical line and tangent line, right? So this will be x4. So you can see that the root is located here, right? We start from x0, which is close, actually not far away from the root. However, after the first several iterations, we are not moving closer to the root, and actually the iterations progressively diverge from the root. So this will, if you continue this process, it will never converge. All right. Then I give you another example. So let me see, x, y, and so this function, for example, looks like this, right? So the root is located here. Assuming that we have initial guess x0, x0 is here. So this is the initial guess, and we want to find the root here, right? So then you draw a tangent line to the function. So this will be x1. And from x1, you draw a vertical line, right? So this will be the intersection point, and then from the intersection point, you draw a tangent line. So this will be x2. And then from x2, you draw a vertical line, and then a tangent line, which is x3. And then from x3, draw a vertical line and tangent line, which is x4, right? So the root is here, right? And after the first few iterations, we are not moving closer to the root. And this illustrates the tendency of the Newton-Raphson method to oscillate around a local minimum or local maximum. So in this case, it's a local minimum, and the Newton-Raphson method is oscillating around this point. Okay, and then we show you another example. So we have a function x, y, 0. So it looks like this, right? And we start from the initial guess here. So let me show you a different function. So for example, it looks like this, right? And we start from the root is here, right? We start from the initial guess. Let me show you, right, like this. So this is the root. Okay, so this is the root. We start from a initial guess, for example, x0. Then we draw a vertical line, and we find the intersection point, and then we draw the tangent line right here. So we get, based on x0, we get x1. And x1 happens to be, if you draw the vertical line, this vertical line will intersect with the function at this, exactly at this local minimum. And then when you draw the tangent line, this tangent line will be exactly a horizontal line, right? So this will be parallel to the x-axis, and you will never find the next intersection point, right? So if that happens, it will never converge. So this is f, the derivative at fx1 equal to 0. So you have this division by 0 problem, right? If that happens, you this method, you can change to another initial guess or change to another method. Okay, so this is the halting condition for Newton-Raphson method. In the next video, we will talk about how to implement this method in MATLAB.